Everyone, this is Mohammad Saibin Ambar Prohor again with another session, and this session is on challenges of machine learning methods, which are overfitting and underfitting. So today we are gonna talk about most talked about machine learning challenges, overfitting and underfitting. So let's get into the session. So we're gonna talk about introduction, train, test, and validate, overfitting, underfitting, solution, and conclusion. So at first we are going to talk about various data sets and how we use those data sets for to use those in our model. At first we are going to talk about the sets and overfitting and underfitting, and then we're going to explain those by drawing sketches and other stuff. So let's get into it. So at first we're going to talk about training set. So training set is the portion of the data set used to train the model. It allows the model to learn the underlying pattern and relationship in data. Typically, it compromises to 60% to 80% of the total data set, which is true. And moving on to the validation set, the validation set is used to tune the model's hyperparameters and evaluate its performance during training. It helps in selecting the best model and preventing overfitting. Usually makes up about 10 to 20% of the total data set. And lastly, which is test set. The test set is used to assess the final model's performance after training complete. Training is complete. It provides an unbiased evaluation of the model's ability to generalize to new data. Typically, it constitutes 10 to 20% of the total data set. So when we train a model, we feed it the training data, and after that we feed it the validation data. So we must isolate the test data while training or keep it unseen so that the trained model can face anomaly of the datasets. This is to ease the difficulty to face real life data. So when we use the trained data, we show it scene side of our real life scenarios, and we use validation data to give the model some seen sites and some unseen sites. So by repeating the validation, we make the model more efficient and more accurate. And lastly, when we feed the test data or the test data set, it actually face various anomalies and various problems which it can face in real life. So in real life, we can't define accurate data. So we have to use this test set to evaluate the machine's accuracy and performance. Let's move on to the theory of overfitting and underfitting. So overfitting occurs when the model learns the training data too well, including noise and outliers. So when the training data is fitted very well, it doesn't care about the test set. This leads to poor performance on validation test sets. Then regularization techniques and proper validation can help to mitigate the overfitting. Moving on to the underfitting. Underfitting happens when the model is too simple to capture the underlying patterns in the data. It results in poor performance on both the training and validation sets, increasing model's complexity and ensuring adequate training can reduce underfitting. So let's move on to the explanation. Mm, Let's say when we get a whole data set like this, we divide it into three data sets. One is train, one is validate, one is test. So almost let's say 70% of data is in the train data set. Then almost 20% almost 20% of datasets are invalidated datasets, and almost 10% of datasets are in test datasets. So we divide the data in these three datasets to train our model. So at first we use train and validate to train our model. So our first step is to use the train datasets to fit our model. It gives us train accuracy, and after that, with this accuracy, we compare our validation dataset by feeding it to our model, and it gives us validation accuracy. So by combining it, we get an average accuracy of our whole training and validation dataset. And after the training, we take this model here and then feed it the test dataset to assess our model. So our model takes the last 10% of the dataset and then gives us the final accuracy, which is the test accuracy. And then we can judge model's performance or model's situation by getting out the accuracy. So what is underfitting and overfitting in this case? So when our model gets the data, let's say the circles are train and the squares are test. So this is the graph, and this is our test datasets result. So this is the final accuracy of the model, the accuracy of our model. And in this case, we can see that our training accuracy, our training accuracy our training accuracy is low. Our test accuracy is also low. So this is the example of underfitting. This is underfitting, and we can see that the bias here is very high because the final result did not touch the test set as well as the training set. So the bias is very high in case of underfitting. And now moving on to the overfitting, this is our training data and this is the test, and the accuracy or result will be like this. As you can see that our training accuracy is very high, but our test accuracy is very low. So by judging by the graph, we can actually see that it did not touch any of the test data. Rather, it fitted too well with the training data, and this is called overfitting. And in this case, variance is very high. In case of underfitting, the bias was very high, but in case of overfitting, the variance is very high. So you can think that what would be the optimal solution for a underfitting and overfitting case. So let me show you a good model or good trained model, which we can call a good fitting or perfect fitting. So this is our test and train data, and the result will see something like this. Yes. So as you can see that it touched both the training data and test data, as well as it fitted perfectly with the training data as well as the test data. So in this case, our training accuracy is high, our test accuracy is also high. So here bias is low, variance is also low. So this is a example of good fit. So by judging the parameters of bias and variance, we can say that the less the bias, the higher the accuracy, and the less the variance, the higher the consistency. So for a model to be good or perfect, we need to lessen the bias and variance to increase its accuracy and consistency. So if you give example of few models accuracy, we can judge, we should judge what is the good model for our system. So let's say that a model has 90% training accuracy and 50% test, 80% training and 76% test, then 30% training, 28% test, 90% training, 82% test, then 85% and 83% test. So let's judge each model one by one. In this case, our first scenario, it is overfitting, because our training model is highly accurate, but our model in case of test data set isn't that accurate or that consistent. That means this is a case of overfitting. Moving on to second, we can see that our training model is also highly accurate and our testing model also not highly but moderately accurate. So I think that this is a good model but not very good or perfect. Moving on to the second model, we can see that both test and train are very low. So both of these have low accuracy, and which is why it is a case of underfitting. Now moving on to the fourth model, both of our test and train accuracy are very high. So this is a good or almost perfect model. So moving on to the last, we can see that our test accuracy is 85% and train accuracy 85% and test accuracy 83%. So this is also a good model. But which should be the winner? In this case, the fourth model is the winner model because it has a very high training accuracy. In both cases of this and this, we can see that the training accuracy is 80%, 85%, and this is 90%, which is a huge margin because 80% of data consists of training data. And for the test accuracy, it just has a difference of 1%, which is why we can ignore that issue. And this model could be our winner. So to reduce the bias and variance, we can use various tactics. For underfitting, we can use the solution of train in time, then increase its feature, and for example, underfitting is the opposite of overfitting. And as I said that when the model is too simple to learn the underlying structure of data, underfitting occurs. So selecting a more powerful model with more parameters could decrease the underfitting problem, then feeding it better features to learn the algorithm, which is called the feature engineering, and reducing the constant on the model. So when we reduce the content, it increases the training time, which helps to reduce the problem of underfitting. And to solve the overfitting, we can use cross validation and regularization. And this also divides into three problems, which is our lasso, reach, and elastinate. So let's create a scenario to understand what is the main problem of overfitting and underfitting. So let's say that I have a math exam and our exam syllabus is 6 chapters, which is 1, 2, 3, 4, 5, 6. And I took preparation of only 4 chapters, which is underlying meaning of trained data, and let's say it's 80%. And the rest of other test data, which is 20%. So when I went to take the exam, or when I took the exam, the questions came from the other chapters I did not prepare of. So let's say the question was one from chapter 5, the question 2 was from chapter 2, the question 3 was from chapter 6, and the question 4 was from chapter 5. So this question is already gone. This question is already gone. This question is already gone. So our model or our brain was only 25% accurate, and I only got 25 out of 100. So it shows that if my exam included question from only 1 to 4 chapters, I would get 100% marks, which is true, because if the chapters were 1, 3, 4, I would get 100 of 100 marks rather than getting the only 25%. But as it came from chapter 5 and 6, my model fell miserably. So how to reduce this? The best solution is the cross validation or K-fold. So while training, my accuracy gave 90%, 90%, 90%. So validation could be various types of model test for my given scenario. Because before giving the exam directly, I can take various model tests, which can help me to increase my horizon or show various data sets which can come in my exam. So in validation, it came 50%, 60%, and 80%. So when the validation accuracy increased to 80%, now it's ready for test. So right now, then I will go to testing. So this method is called cross validation, and the math for it works like this. So let's say that my k is equal to 4. Then that means there are 4 types of question or for the chapter. So I will validate chapter 1 first, and then train the rest of the chapter. Train, train, and train. And by doing this, my average accuracy was 70%. After that, I will validate, I will train the first, then validate the second, then train the rest of the data, and the accuracy would be 90%. And then train the first, second, and validate the third, and train the rest, the accuracy is 30%. And then train the first tree, and then validate the last. So the accuracy is 90%. So every time the temporary unseen data get shuffled or got shuffled, and my average accuracy would be 70 plus 90 plus 30 plus 90 by 4 will equal 70% accurate. So by doing this cross validation k-fold method, we can increase our system's accuracy, which can avoid overfitting by holding the nth of data set, folding every data by validating using the average as their accuracy. So it helps us to avoid the overfitting problem, and these are the problems we face when training our machine learning models or machine learning. And this was our session for today. Hopefully we'll come back tomorrow with other challenges of machine learning. Thank you for staying with us. Have a great time.